So I will starting chapter today's superconductivity. So there are certain materials, okay? When we cool them, their resistivity suddenly drops to zero.
Not clear, sir.
What happened?
Your voice is not clear.
Voice is not clear. Is it fine now? Okay.
Yes, sir.
Okay. So we know that if we cool a metal, for example, okay. So this is the curve of metal, okay. Rho versus T curve for metal, which shows proportion to T, and at low temperature, it shows T5 of behavior. Okay, this is for normal metal. This is for normal metal. Now, there are some material like superconductor. Okay, if I see their resistivity versus temperature plot. Okay, so at high temperature, they have a normal metal type of behavior, and when you cool them, suddenly what happens? Their resistivity comes down to zero. Okay, so this graph I'm plotting for superconductor, and this is for mercury, okay, whose critical temperature is 4.2 Kelvin. Okay, so superconductivity was discovered. Superconductivity was discovered by Camerling ons, okay, by Camerling ons. So he was working on the sample of mercury, and when he was cooling the mercury, suddenly he observed that at a temperature of 4.2 Kelvin, his resistivity goes to zero. Okay, and this phenomena is known superconductivity. Okay,
But can you explain once more this point, the last point?
so I'm telling, if we cool some metal, not necessarily metals, okay, if you cool some compound, then if their resistivity suddenly drops to zero at some particular temperature T, those material are called superconductors. Okay, so superconductivity was discovered by Camerling ons. He was working on a sample of mercury, okay, and he observed the behavior of mercury, that if he cooling them up to 4.2 Kelvin, the resistivity of mercury becomes zero. Okay, so this was metal, but now most of the superconductor, what we know, they are not metal, they are insulators. Okay, so that we'll discuss later. So that is the basically superconductivity. Okay, now superconductivity is not only resistivity zero. Okay, if your material is in superconductive phase, okay, superconductive phase का मतलब क्या है? When it is below a TC, every superconducting material is characterized by a temperature called TC. Okay, TC is called critical temperature. It's called critical temperature. If your material temperature is less than TC, okay, then your sample, the superconductor will be in superconducting state. Superconducting state. Okay, and as your T is greater than TC, it will again become a normal state. Okay, so it is like a thermodynamic phase transition. Superconductor में thermodynamic, if your temperature is low below, it will show superconductive behavior. Superconductive behavior का मतलब क्या है? Its resistivity will be zero. That is a one thing, but that is not the only thing. The property of superconductivity, the property of superconductor. Okay, so superconductor basically defined by two things. Okay, two main characteristics or two main properties. So number one is called resistivity is 0. Number one is its resistivity is 0 or conductivity is infinite. Okay, below Tc when T is less than Tc. And the second property, it shows perfect diamagnetism. Perfect diamagnetism. Diamagnetism. Okay. So what do you mean by perfect diamagnetism? Perfect diamagnetism means a susceptibility value is -1. Okay. If I plot the M versus H curve for superconductor, this is the magnetization. Okay. And this is the field. If I plot this curve for superconductor, it shows this kind of behavior at superconducting phase. So this is your -M. Okay. This is H. If I calculate X chi, okay, that is M versus H. Okay, that comes out -1. Okay, for
Sir,
superconductor.
in first point, sigma equals to what, sir?
Sigma equals to infinite. Conductivity rho is 0. Conductivity will be infinite. Okay. Now, what do you mean by perfect diamagnetism in terms of field lines? So if you suppose you have a sample, okay, kept above Tc, then the field line will pass through the material. Okay, as you cool them, okay, on cooling, what will happen? All the flux line will expelled inside the superconductor. Okay, so when you cool them below Tc, this is called your Meissner effect. Meissner effect. Okay. So superconductor का मतलब क्या है? Now if someone asks you what do you mean by superconductor, the superconductor has a two essential properties. Then one thing, this resistivity should be 0, and other, it show perfect diamagnetism, that all the flux line should get expelled from the interior of the material. That means the susceptibility value be -1. Okay, so diamagnetic materials are the materials which expel the field lines. If you apply field, it will expel the field lines. And if it's a perfect diamagnet, it will expel completely into the flux line from the interior. Okay, so inside the superconductor, your B is 0. Okay, so Meissner effect means what? Meissner effect means the B inside the superconductor should be 0. Now we know what is B. B is nothing. B is mu0 M plus H. Okay, now if B inside is 0, then this become mu0 equals to M plus H. Okay, and if I write the magnitude only, then this M plus H0, and this will give you, just now I show you, it will give you M upon H value is equals to -1. If you put 0, this means 0, and M equal to -H. Okay, so MH value, it will give you -1. That is that we already discussed. Okay, that is superconductor. Now rho is equal to 0 can be for perfect conductor also. If material is perfect conductor, okay, they can also show rho is equal to 0. So that is not the true test of superconductivity. Okay, if you want to find a material is superconductor or not, the true test of superconductivity is this Meissner effect. Okay, so this test it should qualify. This is a true test of superconductivity. Okay, so let me now show you a difference between a perfect conductor and a superconductor. Okay. So just let me take a perfect conductor. Okay. So I have a perfect conductor. Okay. How it behaves in magnetic field. Okay, this is a perfect conductor, and now we have a superconductor. Okay. So this is my perfect is a conductor sample. Okay. And now it is kept in the magnetic field. It is kept in the magnetic field. Okay. And temperature is T is greater than Tc. Okay. And there is a B is equals to B applied. Okay. There is a B, I'm applying B. And you have a superconductor sample, which is also kept in magnetic field. Okay. T is greater than Tc. Now for perfect conductor, there is nothing like a Tc. Okay, but just I'm comparing for these both. I am defining temperature where T becomes 0. Okay, so now this is T equal to Tc greater than Tc. Now when I cool them, if I cool them, okay, if I cool it below Tc, what will happen? Flux line will be intact. Okay, flux line will be intact. Flux line will not go out expelled if it is T equal to Tc. Okay, and B is equal to B applied and T is less than Tc. So flux line will be still inside there. Okay, inside in B. Now
Somebody's mic is on.
please switch off your mic. Someone mic is on. Okay. Now if I cool a superconductor, okay, what happen? It will expel the all flux lines. It will expel all the flux lines, will show marginal effect when you cool them. Okay, so B inside. Okay, so B inside is 0. B inside is 0. Okay, now what happens if I remove the field? Okay, now if I turn off the field, okay, if I make B applied 0, that is switch off, turned off magnetic field. Okay, if I turned off magnetic field, what will happen? Superconductor, nothing will happen because interior there is no B already. Okay, so as soon as you remove the B, switch off B, okay, then B will be 0. B outside will also be 0. Okay, now but what happens in the perfect conductor when you make B is equal to 0? So if when you make B equal to 0, that is turned off magnetic field. क्या होगा बताओ? परफेक्ट कंडक्टर में क्या होगा अगर मैं B 0 कर दूं तो? Tell me anyone. If I move
There
B,
would be some distortion of the alignment of metals, molecule, or anything. Could be.
whenever you change, whenever there is a flux change, what happens? Whenever there is a change of flux, then what should happen? Tell me.
Change of flux, a rise of electric field.
Very good. Lenz law. Okay. So यहाँ पर क्या है? As you come to T less than Tc, just get T greater than Tc. As you come T less than Tc, all the flux is expelled. Now you make B0. Inside, nothing is changing. Already B0, you turned off, B is still 0. So all the lines disappear in superconductor. Now here what happens? There you cooling, flux line present. Now you are turning off this B. जैसे ही B को टर्न करोगे तो जो मटेरियल है उसके अंदर क्या फ्लक्स है, that flux will change, and whenever there is a change of flux, then by Lenz law what happens? एक electric field will produce, and that will produce a current, and that effect will oppose this effect. Okay, so now what happens whenever you I'm rubbing this one. Okay, now for normal conductor, for perfect conductor, when you make B 0, B applied 0, what happens? The eddy currents will produce. Okay, because you're changing the flux now, so material will produce its own field. Okay, it will produce its own field. So there will be current in the material. Okay, and current in the material will, so this will be your field lines. Okay, So current will produce, and that current will produce their own magnetic field, which will oppose this magnetic field, because now this is a perfect conductor. जैसे ही इसमें इलेक्ट्रिक फील्ड प्रोड्यूस होगा, एक there will be a current will generate, and that current will be keep on moving. Okay, because it's a perfect conductor. So current will not decay easily. There will be surface current that will there produce your own magnetic field. That is the difference between a perfect conductor and superconductor. Okay, when we are when we are pulling them in a magnetic field. Okay, the both have a different behavior. Both have resistivity 0. ये resistivity 0 है, तभी तो इसके अंदर एक बार current produce हो जाएगा. So that will not decay easily because the conductivity is infinite. Okay, so according to Lenz law, here it will be a eddy current will produce. Okay, it will produce your own magnetic field inside this one. So B is not 0 here, but there in superconductor B is 0. Okay, I hope the difference is clear. Okay, so this is I have cooled them in magnetic field. Now
So-
what happened?
So this effect would be shown for every material like a ferromagnetic, diamagnetic, or
No.
paramagnetic. Right.
See, first of things, superconductivity is generally not shown by the material which are magnetic. Okay, superconductivity and magnetism, they are like an enemy to each other. If you have some magnetic impurity in your sample, okay, even though it is a perfect superconductor, so its TC will keep on decreasing, so it will destroy superconductivity. Okay, magnetism. So basically, the superconductors, most of the superconductor what you have today, okay, they all are insulators. Okay, so here I'm talking only difference between a superconductor and perfect conductor. Okay, if there's no perfect conductor, okay, but if you see there's a perfect conductor, so you want to distinguish superconductivity with perfect conductivity. Okay, you say some material is a conductivity infinite, but that cannot be called a superconductor. Okay, superconductor का दो टेस्ट है, एक तो उसकी सिग्मा 0 होनी चाहिए और सिग्मा इनफाइनाइट होनी चाहिए, conductivity should be infinite, then second it should show Meissner effect. That point I'm trying to clear. Okay, so perfect conductor जरूरी नहीं कि super conductor हो. Are you getting my point? So I'm just pointing the thing that superconductor is not only perfect conductor, it is something else also. It shows perfect diamagnetism also. That is the main thing. Okay, theoretical background, they both are not same. Okay, now this is what this was cooling in a magnetic field. Now suppose I don't have a magnetic field, I have this one. A sample is there. Okay, now it is kept on T greater than TC. Okay, now what happens if I apply if I cool them? Now what happens? Let me see the difference in between these two, what how they are different. Okay, so now okay, now if I cool this metal, okay, cool this perfect conductor, okay, what will happen? Nothing will happen. Okay, T is less than TC. Now it has a resistivity 0. Okay, now if I turned on magnetic field, so this is a zero field cooling. Earlier was field cooling, so this is called your zero field cooling. I am cooling in zero field cooling. Now if I apply magnetic field, okay, turn on. If I turned on magnetic field, what will become? Inside there is a no magnetic field in the beginning. Now and this is a perfect conductor, this is at close to 0. If I turned on magnetic field, because this is a conductor, the magnetic field not penetrate inside. Okay, magnetic field now will not penetrate, because you know the skin depth of a perfect conductor is what? How much? 0, almost 0. If your conductivity is infinite, then outside magnetic field cannot penetrate here. पहले केस में तो क्या था, टेम्परेचर ज्यादा था तो रेजिस्टिविटी ज्यादा थी, तो ऑलरेडी इनसाइड था. बट यहाँ पे क्या है, इट इज ऑलरेडी रो 0, सिग्मा इज इनफाइनाइट. So even though you switch on the magnetic field not will penetrate inside. Okay, it will be only this like this, because if the magnetic field go inside, there will be eddy currents. Okay, there should be change of flux. So this material will oppose that oppose the entering of the flux line inside the material. Okay. So the flux line will not penetrate inside the perfect conductor at TDC when it has a infinite conductivity. Okay. Now what happens to superconductor? Superconductor will also show same effect. You cool them T less than TC. Okay, this is a normal conductor. Now here you cool them, it becomes superconductor. Superconductor means now it has a ratio T is infinite plus it is superconductor. It will show Meissner effect. Meissner effect means it's a perfect diamagnetic. Now if you turned on magnetic field, okay, so magnetic field will not go inside, will not penetrate. Okay, that means in zero field cooling both show same behavior. Okay, both superconductor and perfect conductor have identical behavior. Both have identical behavior. That is the point. Okay.
So, so at T less than TC, when we cool the perfect conductor, the resistivity would be 0.
Yes, because perfect conductor है ना, टेम्परेचर डिपेंड करती है. अगर परफेक्ट कंडक्टर है तो उसका रेजिस्टिविटी 0 होना जाना चाहिए. भी आपका रेजिस्टिविटी टेम्परेचर ग्राफ क्या होता है?
Yes.
This is your resistivity temperature graph. This is like this. Okay. Now this is the residual resistivity because your material has a impure. If it's a perfect crystal, perfect conductor, no impurity, then this will go to 0. If it's a perfect conductor, are you getting? T should be 0.
Yes.
So if you very low temperature, the resistivity become almost negligible. Okay. So that is the difference here, and this will become a superconductor. But this is not a perfect diamagnet. This is a perfect diamagnet. So field will not enter here because of this diamagnetic effect. Okay, and here it is different. Here it is a because this is a perfect conductor. So it will due to Lenz law, it will oppose the change of flux inside.
So the eddy currents will be there, na?
That will be only surface. Yes, very
on the surface. Okay.
Surface. Okay. Well, skin depth is very less. Okay.
And you said that perfect conductor and superconductor show same behavior at 0 Kelvin temperature.
Zero field cooling.
Zero field
cooling.
cooling.
Okay. So there is no field here, na? So you're cooling here with zero field. You're cooling in zero field, and earlier there was cooling in magnetic field. Okay. So one is magnetic field cooling and one is zero field cooling. So in magnetic field cooling, they will show different behavior. In zero field cooling, they both show same behavior. That's the difference between these two things. Okay. तो ये क्वेश्चन इंटरव्यू में पूछते हैं. Okay, that's why I have explained this one. Now superconductivity can be destroyed. Okay, superconductivity is a thermodynamical phase. Okay, so it can be reversed. You can bring back the material back to its normal state. Okay, so there are 3 parameters by which you can kill the superconductivity. Okay, so the topic is now what kills superconductivity. What kills superconductivity? So there are 3 parameters. One is temperature. Okay, जो तुमने definition में दिखाई था. दूसरा है you have a critical magnetic field. Okay, then is you have a critical magnetic field, temperature, magnetic field. Okay, so magnetic field also can destroy superconductivity. And then you have a current density. Current density also can, if it's a more than limit. Okay, if temperature is greater than TC, if T is greater than TC, then you can destroy superconductivity. Okay, so if I make a diagram, okay, this is my T axis, temperature axis. Say this is my magnetic field axis, and say this is my current density axis. So I can draw this diagram like this. Okay, so at this point, if my superconductor is kept in H is equal to 0, H is equal to 0, and T is equal to 0, J is equal to 0. No current is flowing. Okay, in the superconductor. Superconductor is zero magnetic field. It is superconductor. So of course your temperature is less than Tc. Okay, but showing superconducting behavior, but there is no magnetic field, no current is flowing. Okay, it's floating. Suppose now you suddenly increase the temperature up to Tc, then it will again come back to normal state. Okay, so that means this much temperature required when H is equal to J is equal to 0. If H is equal to 0 or J is equal to not 0, then you require less temperature. So this is only transition because of temperature. Similarly, if your sample is kept at equal to T is equal to 0, T is equal to 0, and T is equal to 0 and J is no current is flowing, then also if you apply a critical magnetic field equals to a critical magnetic field, that will destroy the superconductivity. Okay. Similarly, if your sample is T is equal to 0 and there is no magnetic field also, if you flow a current of magnitude equal to JC, that will also can destroy a superconductivity because JC is equivalent to the critical magnetic field. Okay. JC is J's current is equal to magnetic field. Current will produce its own magnetic field. If this magnetic field is greater than SC, automatically it will destroy your superconductivity. Okay. Now, this magnetic field, okay, is a function of temperature. I told you this magnetic field, I need zero magnetic field if T is Tc. Okay. If T is less than Tc, then I require some magnetic field. If T is equal to 0, then I require SC. So your SC magnetic field is a function of temperature. Okay. So I can plot this the relation between magnetic field, critical field SC and T. So T equal to Tc, you require at T equals to Tc, you require Hc equals to 0. You require critical field. हाँ.
सर ये चीज की दोबारा बता दो ये HC मतलब
बता रहा हूँ बात करने दो. Okay. If T is equal to 0, you need H equal to H0. Okay. So अभी मैं बोल रहा हूँ कि मेरा सैंपल T इक्वल टू TC पे है, तो H कितना चाहिए मुझे बताओ इस ग्राफ को देख के. H कितना चाहिए?
सब ग्राफ के अकॉर्डिंग H0 है.
H0 चाहिए, मतलब वो तो ऑलरेडी नॉर्मल स्टेट में आ गया ना सैंपल मेरा, तो फिर इसको H चाहिए क्यों? दिस इज अ सुपर कंडक्टिंग स्टेट एंड दिस इज योर नॉर्मल स्टेट. अगर T इक्वल TC पे है तो ऑलरेडी वो नॉर्मल स्टेट में आ गया, तो उसको मैग्नेटिक फील्ड चाहिए नहीं. Now if it is not in TC, if it is in zero Kelvin, then how much magnetic field you require to destroy superconductivity? कितना चाहिए? H naught. Okay. Now temperature somewhere here. Then how much magnetic field require? This much. So the magnitude of magnetic field varies depending on the temperature of the system. So ये तीनों जो पैरामीटर है ये साथ साथ काम करते हैं. अगर 2 0 है, out of 3, 2 or 0, then you require TC. 2 0 you require SC. Another 2 0 you require JC. If all are not 0, then you may require, suppose here TC is not 0, then you require less amount of SC or less amount of JC. Okay. Similarly, if JC is not 0, then you require less amount of temperature or less amount of magnetic field in order to destroy the superconductivity. Are you getting? So these the parameters: critical magnetic field, critical current density. These are the function of temperature. Now, JC is what? What is SC? SC also can be written as current. Current कैसे लिखते हैं बताओ? IC upon 2 pi R. If I a superconducting wire, a current is flowing, it will produce a magnetic field. So SC is your IC. Okay. So IC will be what? IC will be now your 2 pi ISC. और JC क्या होगा आपका? JC will be IC upon pi r square area of sample. So I can write the relation 2 pi hc upon pi r square, okay. So it's cancel. So your jc is basically 2 sc upon r. Okay, so this much of current is required. अगर आप करंट से, टेम्परेचर तो ऑलरेडी वन पैरामीटर है ही, अगर आप टेम्परेचर अगर टी इक्वल टू जीरो पे है, एट जीरो पे है, तो इतना करंट फ्लो करने से सैंपल डिस्ट्रॉय हो जाएगा, इट विल कम बैक टू नॉर्मल स्टेट। या इतना मैग्नेटिक फील्ड लगाने से, इतना मैग्नेटिक फील्ड का मतलब होता है इतना करंट, दोनों दोनों सेम चीज है। इतना मैग्नेटिक फील्ड लगाने से वो वापस नॉर्मल स्टेट में आ जाएगा अगर वो टी इक्वल टू जीरो पे है। अगर टी इक्वल टू टी पे है तो ये सब चाहिए ही नहीं हमको, ऑलरेडी टेम्परेचर वन वेरिएबल इज सफिशिएंट to bring this superconductor into normal state. Okay, अब बताओ इसमें कुछ समझ में नहीं आ रहा तो क्या डाउट आ रहा है बताओ परमप्रीत।
सर एक कंफर्म करनी है चीज सर बस।
हाँ
सर एट t equals to 0
हाँ
we need this this you have written the amount
this if t is equal to 0, अगर मैं करंट भी फेज ट्रांजिशन कैन हैपन थ्रू करंट, थ्रू मैग्नेटिक फील्ड, थ्रू टेम्परेचर, कोई भी एक वेरिएबल हो सकता है।
ओके सर।
बट देयर वैल्यू डिपेंड ऑन टेम्परेचर।
ओके सर।
तो अगर ये 0 है तो इतना मैग्नेटिक फील्ड लगाना पड़ेगा।
ओके सर।
Okay, but h0 is what? So let me write here.
देन दोनों चाहिए ना, जेसी एंड एचसी दोनों होंगे।
दोनों नहीं चाहिए, एक से हो जाएगा ना,
एक से ही हो जाएगा अगर एचसी 0 कर दें और टीसी भी 0 हो जाए।
तो फिर किससे फिर करंट करना पड़ेगा भी सैंपल में, या तो करंट भी सैंपल के ऊपर, या तो मैग्नेटिक फील्ड लगाओगे भी दोनों भी सैंपल में भी। सैंपल मेरा ये एकदम कूल हो रहा है, कूल हो, सुपर कंडक्टर बन गया। सुपर कंडक्टर होके सपोज ये लिक्विड नाइट्रोजन में पड़ा हुआ है और ये फ्लोट हो रहा है, इट शोइंग माइजर इफेक्ट। माइजर इफेक्ट का मतलब क्या, ये फ्लोट करता है मैग्नेटिक फील्ड में। अब इस पे ये ना तो करंट है ना तो मैग्नेटिक फील्ड है। अब अगर आप मैग्नेटिक फील्ड लेके आ जाओगे या ये टेम्परेचर बढ़ा दोगे तो अपने आप ये नॉर्मल स्टेट में आ जाएगा। ओके
ओके
ओके, कितना टेम्परेचर चाहिए? टेम्परेचर चाहिए टी इक्वल टी सी, बस।
ओके सर।
तो कोई भी एक पैरामीटर लगाने से आ जाएगा। सो दिस इज योर, so this is h0 is what? h0 is critical magnetic field, critical magnetic field at t is equal to 0 Kelvin. Okay, and you require sc. Okay, so this is sc equal to h naught. Okay, sc equal to h naught at critical magnetic field. Okay, and you require critical magnetic field value 0 if sample is at t is equal to tc. That is the meaning. Okay, now there are some theoretical backgrounds. Okay, so let us explain the superconductivity using why superconductor show this kind of behavior. How can we explain and this behavior? Okay, so this behavior का मतलब है कि एक तो zero resistivity and दूसरा B inside is zero. That is perfect diamagnetic behavior that we have to explain with using some theory. Okay, so the first attempt was done by London. Okay, so put the heading now, London equation. London equations, or you can write that electrodynamics of superconductor. Okay. So now how can we explain these two properties? Okay, so London equations are based on two fluid metal. Okay, so London equations are based on two fluid model. Okay, two fluid model. Now what is two fluid model? Now two fluid model का मतलब है कि this model says, so there are two type of electron. Okay, one is called super electrons inside the material. Okay, you have a super electrons, okay, which move without frictionless, which do which move without any friction, without any friction. Okay. And then in the electric field, okay. And other is you have a normal electron inside a superconductor, normal electrons, okay, which get scattered, okay, like ordinary electron, like ordinary electrons. So the theory is explaining, okay. Now in a superconductor there are two types of electrons, super electron and normal electron, okay. And this super electron form Cooper pairs. Super electrons form Cooper pairs. They form pairs which do resistance-less motion, or which do not get scattered. Okay. So you have N equals to the current, the carrier concentration is equal to Ns plus N normal. Okay. So this is the Ns is the carrier concentration of super electron, and Nn is the concentration of normal electron. Okay. Now Ns to N becomes equals to become Ns when T is equal to 0 Kelvin, and N become Nn when T equals to Tc. Okay. So basically ये क्या बता रहा है ये मॉडल कि इसमें दो तरह के फ्लूइड फ्लो करते हैं सुपरकंडक्टर में, एक सुपर इलेक्ट्रॉन फ्लूइड, एक नॉर्मल इलेक्ट्रॉन फ्लूइड. The concentration of super electron and normal electron depends on temperature. If you are at T is equal to 0 temperature, जितने कम टेम्परेचर पे TC पे उस पे उतने ज्यादा सुपर इलेक्ट्रॉन होंगे, और जितने भी सुपर इलेक्ट्रॉन है they remain in the form of Cooper pairs. The Cooper pair moves with the frictionless motion. If you as you increase the temperature, what will happen? That all the electrons slowly convert into normal electron, because these has a Cooper pair, they have some binding energy, and if you heat them above their binding energy, what will happen? These Cooper pair will break and they will become a normal electron. So that is the basic assumption of this model. Okay.
So what is super electron?
Super electrons are वो electron that move without any friction. Okay. Which they move with a frictionless motion. So जो scattered नहीं होते हैं, that remain in the form of Cooper pair. Okay, we'll discuss in Cooper pair in basis theory. Super electron form Cooper pairs, and the Cooper pair do not scatter with the lattice, like we have seen when electrons are moving in a lattice. We have calculated this Dudes theory. At that time we told there is a opposing force is acting on the electrons, and electrons get scattered with the lattice. Okay, but in the case of super electron, these electron do not scattered by lattice. Okay, that's why these electrons are called super electrons. Okay, now let us write the equation of motion for these electrons. So now I have to explain two properties. One is resistance-less motion, and then second is we have to show that magnetic field cannot penetrate inside a superconductor theoretically. Okay, so now I'm going to show these two properties using these London equations. Okay, electrodynamics of superconductor. So now if I write equation of motion for super electrons, equation of motion for super electrons. Okay, so how can I write? I can write m acceleration force dv upon dt is equals to what? Force कितना होता है? Force will be your E into E, magnitude everything only, acceleration. And when we have written the normal electron, that time I have written here is a opposing force which is proportional to velocity minus gamma v also. And I was writing the normal electron Okay, there was a term involved which is corresponding to scattering. Okay, which is reducing the speed. Okay, so that term is not present here because these material do not get scattered. Okay, so for super electron, this is the equation of motion. Now, you know, if you have n equal to ns plus n equal to normal, if I write the current density in superconductor, that is equal to Js plus Jn. Okay, and Js current is proportional to velocity, that is nves. Okay, that is nves. So here I can write my J equal to nevs. Okay, now if I put the differentiate this one, Js djs upon dt. If I do this one, this will be equal to ne dvs upon dt. And now, if you put the value of dv by dt in this equation, that will give you the first London equation. Put the value and tell me what is the equation. So suppose this is my equation of motion. Okay. Now, if I write dgs upon dt, that gives me ne, and this gives me e upon m. E upon m. So d delta js upon dt, this gives me ne square e upon m. So this is the first London equation. This is called first London equation. Okay. Now I want to explain zero resistivity or zero resistivity. The first property, zero resistivity. Okay, and a zero resistivity can be explained by this equation. So if you have a why superconductor have a zero resistivity, so you have dgs upon dt and you have a ne square e upon m. Okay, now from this equation, what I can write, if E is 0, electric field is 0, this implies what? Del Js upon del T equals to 0. And this implies that Js equals to constant. Okay. And this equation suggests that without any external field, a current can exist in superconductor. Without any field, and current can exist in a superconductor, and that current is called persistent current. Persistent current. Okay, what does this mean? See, अगर अपने पास में एक सुपर कंडक्टिंग सपोज रिंग है, ओके, और उसमें मैंने इलेक्ट्रिक फील्ड लगाया, तो उसमें करंट प्रोड्यूस हुआ, एंड देन आई रिमूव द इलेक्ट्रिक फील्ड, तो क्या होगा? अभी उसके अंदर क्या है, करंट फ्लो करेगा कि नहीं करेगा, बताओ?
करेगा सर,
करेगा ना, because the resistance is 0. So once you have introduced current in the superconductor, and even though the external field is 0, the current will be keep on moving, and there is a samples in the laboratory where current has been given 30 years before. अभी तक उसमें current flow कर रहा है. Are you getting?
yes sir.
Because why? Because the resistance is 0. So they are moving, electrons are moving frictionless. Okay, that's why this model says there are two type of electron. One is called your super electron, the other is normal electron. And using the super electron theory, that they are not scattering, we can explain that current can exist for many years, that is resistivity is 0. Okay, current can exist for forever in superconductor where electrons are moving frictionless, and this suggests the resistivity is 0. Okay, this first property is explained using London equation. Okay, now the second property we have to explain why superconductor do not allow the magnetic field to enter inside it, or why they repel the magnetic field. Okay, that is B inside should be 0. That we have to explain using the superelectron theory. Okay, now the first is this one. Now you have the equation, this one. Now I'm using the same equation in order to write the second London equation. Okay, so so I'm going to write now second London equation. Okay, so in order to write second London equation, write E from here. So what is the value of E? So E will give you what? E will give you M upon NE square djs upon dt. Okay, now let me take curl of this one. Okay, so del of E. Okay, if I take del of this one, this will give me M NE square d upon dt, or del upon dt. What do you run? This will give you del cross JS. Okay, this will give you del cross JS. Okay, so give some equation number here. Okay, I'm doing like this. Okay, so this is del cross JS. Now I want to find what is the value of del cross JS. Del cross E already I know. Del cross E is you're already that is del B upon del T. Maxwell equation. This is M, this is NE square. It is d upon dt del cross JS. Okay, now del cross J I can write from fourth Maxwell equation, which says del cross J can be written as a mu zero. What is the what is the value of del cross J? Tell me from Maxwell equation. What is the fourth Maxwell equation? The fourth Maxwell equation says del cross B is equals to mu 0 J, if it is super electron J plus JD. Where is the what? JD is what? What is JD?
Displacement current.
Displacement current density. Displacement current density. Okay, and which is equals to 0 for superconductor. Okay, we're negligible for superconductors. So we don't have a displacement current density in superconductor. So simply you can write your del cross B is equal to mu 0 JS for superconductor. Okay, put this value here. So if I put this value here, okay, what it will give me? It will give me minus del B upon del T M NE square d upon dt del cross B. Okay, and this del I can cancel out. Okay, so my d will be simply M upon NE square del cross B. Okay, this is my simple. Okay, now what you can write here from here. Okay, so this is your here. This is itself. If I remove this dt, this will give you second London equation. Okay, but I'm not writing this way. We'll change later. So del cross JS is basically del cross JS is equal to B into Ni square upon M. This is the second London equation. If you want, you can write from here del cross JS. I will modify that one, so I didn't write minus ne square upon m. Okay, b. That is your second London equation. Second London equation. Okay. Now this is your b equals to del cross b. Okay. Now I want to write this as a b m upon ne square, and this can be written as a del dot b minus del square b. Okay. Now if you write
Sir, one minus will be there na in front of B.
यहाँ पे, हाँ b के माइनस है ना, तो बीच में माइनस में यहाँ कर दो, ठीक है, b इधर कर दो, माइनस इधर कर दो.
Okay.
So del dot b is 0. So del dot b is 0. Okay. So you can write your b is equals to minus minus plus. This will be m ne square. Okay. Del square b. Del square b. Okay. So am I missing this mu 0? Mu 0 भी तो आएगा ना? Here when I put a JS value, that mu 0 also should come here. Mu 0. Okay. यहाँ से क्या आएगा? JS delta cross b by mu 0. So mu 0 भी तो आएगा यहाँ पे. This is mu 0 also there. Okay. Mu 0. This is your mu 0. And if I write in 1D, okay, or you itself, here itself you can write this b is equals to lambda L square, okay, del square b, okay, where lambda is called your lambda L is equals to m upon ne square mu naught, okay, m upon ne square mu naught is called penetration depth, is called your penetration depth. Okay, how much magnetic field हाँ
So it was mu naught JS ना?
हाँ म्यू नॉट जेएस था ना, जेएस की वैल्यू पुट करी ना हमने,
तो
तो 1 by म्यू नॉट ही आएगा, 1 by म्यू नॉट डेल क्रॉस बी.
oh yes, yes.
Okay, so this is your, so this is penetration depth. Okay, now let me write this equation in 1D. Okay, so I can write in 1D, this equation can be written as a b upon lambda L square del 2x upon del 2b bx upon del x square. Okay, and del 2b b to खाली. Okay, del 2b upon del x square will be b upon lambda L square. Okay, lambda L square. Now tell me the solution of this equation क्या आएगा बताओ, इस equation के solution क्या आते हैं? Second order equation. What is the solution of this equation? ये तुम बार-बार यूज करते ही हो.
Sir, exponential decaying आएगा.
Exponential decay आएगा, solve करोगे तो bx क्या आएगा? bx will be your a, okay, x upon lambda L plus b e power, और यहाँ पे तो a minus and b positive, a positive, okay, okay, whatever you want to write. Okay, a is negative, b is positive. Okay, b x upon lambda L. This is the solution of this equation. Okay, now if you say, if I say x is equal to 0, this is lambda upon L or x upon L? Tell me, क्या आएगा? Yes, equation ठीक है, x upon lambda L.
Yes, sir.
Okay, so if I say my x is infinite, okay, x क्या है? Depth है inside the superconductor. If I say my x is infinite, that time what b will be what? 0. If I put x equal to infinite, okay, so this will give you, this term will become 0, and this give you b infinite, which cannot happen. So if it's x infinite implies, so this is b infinite, okay, this implies b infinite, which cannot happen. So this implies your b should be 0. So b should be 0. Okay, so the solution should be like this only, exponential decay. So your, so this will be your now b equals to a e power minus x upon lambda type of solution will be there. Okay, now here you can define the penetration depth lambda L. Okay, so penetration depth lambda L. Okay, so is equal to the, so what is the definition of lambda? Tell me now, what is the definition of lambda? How can you, 1 by e, na? The distance at which, okay, magnetic field becomes okay 1 by e of its value surface में x0 value, its value 1 by v of its value at surface. Okay, that length is called, that distance is called your penetration length, penetration depth, or penetration length. Length is better. Okay, length is the penetration length or penetration depth. Okay, so that's the definition. Distance at which the magnetic field becomes 1 by t of is its value at surface. Okay, that will be your, so I can write, if is x is L, then your dx will be what? Dx will be b of d by e. Okay, so this will be basically what? b0 of b. If I put x equal to 0, okay, this will become 1, this become bxa, that is b0. Okay, you can write this equation also. If you put x equal to 0, then b0, so this equation also can be written as a b equal to b0 e power minus x upon lambda L. That equation also you can write like this. Okay, and this will be your definition of. That means what will happen if you are moving inside a superconductor? Okay, you will, your magnetic field will decay with distance. Magnetic field will, so here you have magnetic field outside. As you are moving inside the superconductor, this will decay, and this becomes depending on the value of lambda. How much is lambda? Okay, if lambda is very low, okay, suppose lambda is an angstrom, 100 angstrom. So if you go inside up to 5 angstrom, okay, this term will become 0. That everything depends on lambda. So penetration depth agar kam hai, if you suppose this is only this is generally in order of nanometers. Okay, so 100 nanometers, and this is your 1000 nanometer. So that is 10 times of this one. So this becomes 0. Generally, the skin depth that is comes in micrometer, because this is in 100 of nanometers. So skin depth is micrometer. So your sample only can penetrate up to only micrometer distance. Inside it cannot penetrate. That is inside B0. That is your what are we saying? Meissner effect. Okay, or B inside is 0 in the field. Okay, that means if x is greater than lambda L, your in this equation, okay, your b will become 0. B inside will become 0. Inside will become 0. Okay, that is what? That is magnetic field cannot penetrate in superconductor, because it is superconductor के electrons लिखा है for superconductor. Okay, That is perfect diamagnetism. That is called perfect diamagnetism. Perfect diamagnetism. Okay. That means we are able to explain both the properties rho 0 and perfect x equal to -1 perfect diamagnetism using this London equation by doing simple electrodynamics. Okay. So I'm stopping here. If you have a question, you can ask me. And now if you want, you can write the second London equation in terms of lambda L also, जहाँ पर जो हमने लिखा था delta cross JS. Okay. Second London equation. There you can write now minus b upon mu 0 upon L square minus b upon mu 0 upon lambda square. Okay. So this is another form of second London equation. This is also second London equation. Second London equation.
So,
Ah.
so which part is to be focused for the exam purpose?
The exam दो पॉइंट है. एक तो आपका एग्जाम है, रिटन एग्जाम है. ओके. और रिटन एग्जाम में क्वालिफाई करने का मतलब नहीं है कि आपको पोजीशन मिल जाएगा. ओके. देन देयर इज अ सेपरेट पार्ट इज इंटरव्यू. सो दोनों पार्ट के लिए आपको कैलकुलेशंस भी करनी है, आपको थ्योरी भी जाननी है, आपको इंटरव्यू में बताना भी है. तो तैयारी तो दोनों की करनी पड़ेगी. ओके. रिटन के लिए जैसे हमने डेंसिटी स्टेट्स किया ना, आपका जो लैटिस वाइब्रेशन था, लैटिस डेंसिटी स्टेट करना, फ्री इलेक्ट्रॉन थ्योरी, तो जो क्वेश्चन मास इफेक्टिव मास निकालना, वो सारी चीजें आपको आनी चाहिए. वो उस पे एग्जाम में क्वेश्चन आते हैं. सुपरकंडक्टिविटी में थ्योरेटिकल क्वेश्चन आते हैं. आप प्रीवियस ईयर के क्वेश्चन देखो. ओके. तो फोकस जितना सिलेबस, तो वो कोई फिक्स तो नहीं कि इसमें से पूछेगा या इसमें से पूछेगा. और छोटा सा सिलेबस ही है. अगर आप फाइनली आप अपनी कॉपी के थ्रू जाओगे तो यू कैन रिवाइज दिस कॉपी विद इन फ्यू आवर्स. ओके. अभी जितना भी आपने कराया है उसको अगर आप वापस जाके देखोगे एक बार तो बड़ा जल्दी रिवाइज कर सकते हो. तो तैयारी तो आपको पूरा ही करना है ना. कोई ऐसे तो नहीं कि ये टॉपिक में से क्वेश्चन आएगा या उससे आएगा, पता थोड़ी है. और वो सिलेबस बहुत बड़ा भी नहीं है. तो एक तो रिटर्न की तैयारी करनी है.
मैं इसी थ्योरी के बेसिस पे पूछ रही हूँ. ये जो लंदन थ्योरी की है, इसमें कौन सा किस प्रकार का क्वेश्चन होगा?
इसमें कोई क्वेश्चन नहीं. इसमें तो खाली एक थ्योरी है कि बीच में आपको पूछ लेगा ये फर्स्ट लंडन इक्वेशन क्या है, सेकंड लंडन इक्वेशन क्या है, पेनिट्रेशन डेप्थ क्या है. ठीक है. अब यहाँ पे जो पेनिट्रेशन डेप्थ निकल के आया है, इस पे आगे क्वेश्चन बनेंगे. इसकी आगे इस थ्योरी आगे जाएगी अभी तो. ठीक है. यहाँ पे जो पेनिट्रेशन डेप्थ वो सब ये सब कैरेक्टरिस्टिक्स है ना सुपर कंडक्टर की. आपकी जो पेनिट्रेशन डेप्थ हो गया, कोहेरेंस लेंथ हो गया, ये सब तो कैरेक्टरिस्टिक सुपर कंडक्टर की. तो वो उनकी वैल्यू कितनी है, किस सुपर कंडक्टर की कितनी वैल्यू है, that all you have to keep in mind. ओके. तो ये तो जस्ट एक सिंपल इलेक्ट्रोडायनेमिक्स है कि जो हमारे सुपर कंडक्टर को एक्सप्लेन कर रहा है. इफ आई से इट इज अ टू फ्लूइड मॉडल एंड दो तरह के मॉडल है और जो सुपर कंडक्टर ड्यू टू सुपर इलेक्ट्रॉन, so I can explain this two properties. That is theoretically only, theoretical background. Okay. So the question can be asked on super electron, what difference in equation motion of super electron and normal electron. Okay. तो theoretical question बनते हैं, जो पढ़ा है उसी में से कुछ पूछेगा बीच में से. हाँ. Yes.
सर एक बार आप मुझे बताएंगे पेनिट्रेशन डेप्थ और कोरिलेशन बिटवीन मैग्नेटिक इफेक्ट एंड पेनिट्रेशन डेप्थ.
आपका जो मैग्नेटिक फील्ड है, मैग्नेटिक इफेक्ट क्या है? Tell me what is मैग्नेटिक इफेक्ट? What is the Meissner effect? कौन पूछा था क्वेश्चन अभी? What is Meissner effect? Meissner effect is.
सर मैंने ही पूछा था सर. एक्चुअली क्या स्टार्टिंग में थोड़ा सा मैंने क्लास छूट गया था.
हाँ, तो Meissner effect is your B is equal to 0 inside. Okay. The superconductor expelled all the flux line. Superconductor के अंदर superconductor behaves like a perfect diamagnetic. मैं 10 बार तो बोल चुका हूँ मैं. Perfect diamagnetic. Okay. The flux line will expelled out of this one. So B is 0. Now same thing. This concept is saying London equation saying that as you go move above lambda L, jitna lambda, suppose lambda is 100 angstrom, and if you go 1000 angstrom inside the superconductor, that B will decay with distance. B will decay distance, and finally it will become 0. तो inside B कितना है? 0 ही है ना. ये आपका 1/E. Okay. This is your 1/, this is your penetration of lambda L. तो यहाँ पे आपका B जो है, B is equal to जो सरफेस पे है ये वाला, इसका 1/e है। अगर इसके आगे जा रहे हो तो ये ड्रॉप होता जा रहा है। नाउ इफ इट इज 100 एंगस्ट्रॉम, ओके, and you go up to 1000 angstrom, 10 time of this one, okay, then it will be zero, almost zero. That means field only can penetrate only surface up to micrometer length, okay.
Yes, sir.
So that is Meissner effect, but it is showing opposite. It is showing like it's like explaining like a perfect conductor, okay. That means this theory is not sufficient, okay. We have seen what when a field inside it can get expelled. It's saying field cannot penetrate. If it's your superconductor is superelectron, field cannot penetrate. But the same thing happens in perfect conductor also. In the beginning, I show you difference. Okay. So that's why otherwise we'll stop here. Okay, this theory is sufficient. This is not end of the theory. Okay, we need other theories also. So this is the first attempt to explain the superconductivity is London. Okay.
So what you said about when
Okay,
lambda
sir.
is small,
Huh?
lambda is large, then bx would be 0 inside. But when lambda is small.
ये क्या x क्या penetration depth है?
Okay.
जैसे जैसे ये लैम्बडा एल से ज्यादा होगा, लैम्बडा एल पे 1/e हो जा रहा है, ओके 67%। अगर आप 2 लैम्बडा एल जाओ, 3 लैम्बडा एल जाओ, 4 लैम्बडा एल जाओ, तो क्या हो जाए, 5 लैम्बडा एल जाओ, 10 लैम्बडा एल जाओ, तो जीरो नहीं हो जाएगा इस इक्वेशन से? अगर
So
मैं हाँ फिर
that is for lambda L is greater than lambda L is large, ना?
लैम्बडा एल इज वैल्यू कितनी है वो पता होनी चाहिए ना। दैट वैल्यू इज 100 एंगस्ट्रॉम जनरली, 100 to 2 एंगस्ट्रॉम, मतलब इफ यू 100 एंगस्ट्रॉम है, इसको तुम भूल जाओ ना, ये कुछ भी है, ये सपोज ये एंगस्ट्रॉम में है। अगर ये e⁻10 हो गया या e⁻5 हो गया, तो e⁻5 ये पूरा जीरो नहीं हो जाएगा?
Yes.
तो इसका अगर 5 टाइम्स भी है तो ये तो एंगस्ट्रॉम में है। इसका मतलब माइक्रोमीटर पेनिट्रेशन जो होता है वो माइक्रोमीटर डिस्टेंस तक ही होता है सैंपल के अंदर, अंदर B0 है। ओके so I'm stopping here. Any question? परमप्रीत क्लियर है कि नहीं है?
सर मैं कंफ्यूज हो गई ये चीज में।
हाँ तो बताओ, पूछो ना, जब क्या कंफ्यूजन है?
पर यही डेप्थ में।
हाँ तो डेप्थ क्या है? डेप्थ x है और
यस सर।
लैम्बडा एल क्या पेनिट्रेशन डेप्थ है। अगर डेप्थ पेनिट्रेशन डेप्थ का 5 टाइम्स है तो जीरो हो जाएगा। ये ग्राफ शो नहीं कर रहा है यहाँ पर, ये ग्राफ देखो, ये ग्राफ देखो, यहाँ
सर
पे यहाँ फील्ड कितना है B/E, ये जीरो पे कितना है फील्ड, सरफेस पे कितना है, ठीक है।
यस
फिर आप अंदर जा रहे हो लैम्बडा एल तक, ये B/E हो गया।
यस
नाम पेनिट्रेशन डेप्थ है, इसका मतलब नहीं कि कल खाली पेनिट्रेशन डेप्थ तक जाएगा। ये एक लेंथ है
ओके
जो 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 बताती है कि इसके आगे इतने पे आके इतना हो जाता है फील्ड। अगर
यस
इससे आगे जाओगे तो जीरो होता जाएगा, ये बता रहा है।
ओके सर।
पेनिट्रेशन डेप्थ का मतलब ये नहीं कि इतनी लेंथ तक ही पेनिट्रेट करेगा। ये कहा मैंने डेफिनेशन लिखी, द लेंथ एट विच B becomes 1/E of और सरफेस मैग्नेटिक फील्ड, और उसके आगे जाओगे तो जीरो हो जाएगा।
इससे पीछे तो बी होगा ना समथिंग, इससे पीछे पीछे।
इससे पीछे तो B तो बाहर तो है ही ना, आउटसाइड तो B है ही है, सरफेस पे तो B है ही है।
सर ये सरफेस और लैम्बडा के बीच में।
हाँ यहाँ पर
यस
यहाँ पर धीरे डिक्रीज हो रहा है ना। यहाँ पर भी फील्ड तो यहाँ पर भी है ना, अभी फील्ड तो ये मैक्सिमम है जीरो पे, फील्ड तो यहाँ पर भी है। फील्ड जीरो कहाँ हो रहा है, यहाँ तक जाकर जीरो हो रहा है।
ओके यस सर समझ आ गई।
पर ये पेनिट्रेशन बहुत हाई नहीं है, ये माइक्रोमीटर में ही है, क्योंकि ये एंगस्ट्रॉम में ही है। अगर 10 तक जाओगे तो जीरो हो जाएगा, तो मतलब पेनिट्रेशन अप टू माइक्रोमीटर में ही है, और माइक्रोमीटर में तो है तो अंदर तो जीरो ही है फील्ड। ओके लक्ष्मी बोएला,
Yes, sir.
क्वेश्चन?
Yes, sir.
हाँ
So penetration depth means ऐसा डिस्टेंस है जहाँ पे मैग्नेटिक फील्ड 1/E फैक्टर से डिक्रीज होता जाएगा।
यस दैट्स डेफिनेशन।
सर तो लैम्डा एल का जैसे आपने बोला ना सर कि ज्यादा नहीं है वैल्यू, तो मतलब कितना वैल्यू है अप्रॉक्स?
हम वो बता रहा हूँ ना, 100 एंगस्ट्रॉम से कुछ मटेरियल का 500 एंगस्ट्रॉम तक होता है, तो 100 to 500 एंगस्ट्रॉम है। ओके
ओके
जितना जितना अच्छा सुपर कनेक्टर का उसके लिए उतना कम होगा ये।
अच्छा
ठीक है
Thank you, sir.
Kishore,
Yes, sir.
question?
सर समझ आ गया सर.
Okay.
Thank you, sir.